should probably be around. Yeah, that's my plan. I don't. Yeah, I think planning to be around something on 15. So yeah.
Like we already so that's something works large. You try to estimate that's just
Yeah.
We were thinking that what we do, like basically we just use the social media cluster all of the tracks. Just like
Okay.
and then also cluster every like so like if the track has like the track had 10 nodes
Yeah.
and you did 2 grams, then every track's first 2 nodes would be clustered, and every track's like 7 nodes would be clustered until
Okay.
you ran out of the nodes in a track, and it just would be clustered
Okay.
up to like all of the tracks. Eventually, I mean, there would be a few probably that it was like just 2 tracks being clustered or something, if there were like 2 really tracks or something.
Yeah. Yeah, when it hits some sizes that makes it yeah, what you might try and do is to have a non-symmetric difference where you can think of this assignment-based cluster where the center is like a short snippet. And so if this snippet shows up in any of the tracks, so it's not symmetric because you wouldn't put a long track to match to a short snippet, the same snippet.
So, like, I think you're saying you want to be able to identify any snippet as the same region as the snippet.
Well, you want to identify some snippet that comes up in a lot of trees, and that's a center. If there's like a catchy theme that or a repeat of some notes that shows up in a lot of tracks, that makes those tracks centered around that.
That's what I was thinking, and maybe this isn't going to do it, but wouldn't that be what the K-grams would be? Like if you have the K-grams,
If you use the
so many
K-gram
nodes.
as the center of a science cluster,
Yeah, and then cluster the K-grams is what I'm saying.
you could cluster
Find the center of K-grams.
It could. I mean, this might give you something slightly different than what I'm saying. But both of these could make sense. You're clustering the K-grams, and then you want to see which tracks show up in a lot of those K-grams. This is another way to get it. And the point is there are a lot of different experiments on it. Try and explore that'll make it very possible.
The other big variable what if
That's not going to make us, I mean, there's like, if you do everything the same and you think it'll work, there's like, it may prevent you from getting 100 points, so like, maybe there's like a lower bar for things that are out of so it's and even if you try really good things and you really demonstrate, you can still do really, really well.
I mean, I think it would be something cool.
That's, I understand that. So I'm not going to hold it against you. It's just to see that you're going through the right process.
Well, I'll just see the second
Yeah, probably at least 1 or 2 days. Hey, so let's get started. So we got some new screens and projectors. These look great. You can actually see the grid cells. The color green is working. I have 2 of them. So I figure I can burn the actual candles from both ends. I'm not sure if I need to, but I guess just for today, I'm so excited. I feel like using both of them. We'll see how this goes. Okay, so I'm sorry I wasn't able to be here for the midterm, but it's from what I have glanced at them this morning and from what I heard from the Ts, it sounds like everything went great. Yeah, and it seems like people were you know, some people use the whole time, and that's good, but a lot of people were able to finish early, and you know, that's great. I think the midterm was actually harder this year than it was last year, but people took longer last year. So you guys must be kind of you know, like very smart and learning a lot of the material really well. So that's good. Good. So I kind of want to hold off discussions about that till after class. So and if you have any questions about particular questions or something, we can discuss it after class. We'll grade them at some point over break, and so they'll be back to you probably the Monday after break. Okay, so Monday after break also is when your intermediate project reports are due. So you'll have a fun spring break, I'm sure. Well, you know, I've hopefully given you enough lead, but so again, the point of these project reports is I want to see enough stuff so I can tell you this is what you should do towards finishing it to have a good project, right? I want to be able to give you feedback on that. And so that should be your main kind of motivation in trying to work on these reports. Try and give me enough information so I can give you feedback. And so part of what we're going to do on Monday after break is we're going to have like a half class lecture, and then I'm going to assign pairings between groups, and you're going to give each other feedback on your projects as well. Okay, so we're going to do some in-class, even more feedback before I give you some. And so I think this will be important, not just so you're going to get more feedback, but you also will get to see what other groups are doing, and this kind of get a better sense of maybe calibrating what makes sense to be doing, or get some new ideas. And you know, I find, you know, I have certain ideas towards these projects, but all of you are so bright and creative. You'll probably come up with even cooler ideas to give your like all of your classmates. So I think this will work well. Okay, so there'll be. I'll explain how that will work on Monday. But so yeah, so you'll have to talk to these other groups about the project reports. So you'll have to turn them in online through Canvas, but it'll be good to have something tangible to discuss with the other groups. Okay, so whether it's on a computer that you can share with them directly in class, or you print something out, that might also be easier. It doesn't have to be just a project report. You can also just show them what you're doing. You know, I'm flexible in that regard. Okay, a couple other things. Some people had questions about the K medians problem on homework 3, and this sounds like you all had a lot of fun with that question. I don't want to give too much away on camera, so I will be happy to discuss kind of what you could have done after class. So after class, I'll be around, and I'll be happy to discuss some details after we turn off the camera off the permanent record. So people next year can't say, right, if I give a similar question. Okay, so and then I said I'd be taking office hours by appointment tomorrow morning. No one's emailed me. I probably won't be able to make any. My son's sick, and I think I need to stay home with him tomorrow morning. So, but I should be around more or less during break. So if you have questions about projects during break, you can't wait till the intermediate report. Hopefully I can find time to meet with you. Okay, great. So onto the lecture. One more thing. So the notes were updated at the start of the semester up until this lecture. This one is now updated for this semester. The ones after break have not been updated yet. I'll update those probably over break. So if you've been printing them out or something, the new versions will hopefully be up for the rest of the semester by the end of break. Okay. Great. Okay. So we're talking about this matrix sketching, and to kind of again revisit what what this is about is we're thinking of taking this large matrix and we wanted to approximate this using something like this singular value, this, so this, using the singular value decomposition. And remember what that gave you was a decomposition into these three matrices, where this is U, this is S, and this is V transpose. And the kind of the key thing was that the only interesting part of S was along this diagonal here, and everything else was going to be zeros. So what that meant was basically this whole part of U also did not matter because this was all zeros and it got multiplied by this part. So this part didn't matter. And then what you often wanted to do is take, say, the best rank K approximation of A, and what you would do is you would set a bunch of these guys up to 0, and so there are only going to be K things on this diagonal which are non-zero. And what that does is basically this part of this matrix and this part of this matrix, now these are blocks of all zeros too, which makes the lower part here not interesting and also this part not interesting. So the dimension here is only K and the dimension here is only K. And the resulting matrices are then called UK, SK, and VK transpose. And the product of these you're going to get is, we'll call AK is UK, SK, VK transpose. Okay, and you can get the U, S, and V matrices by just calling the SVD operation in Matlab or many other places. And it'll do this, and then you can get this approximate rank K approximation to A, which will again be an n by d matrix, but will have rank K, or the data from d dimensions will now live on this k-dimensional subspace. Okay? So remember, this was what we talked about last week on Wednesday. Okay, so then what is the matrix sketching problem? Well, what we'd ideally like as a statistical sense of what's going on with the data, we're going to think of like these n data points as being observations of some phenomena. And this U matrix is just mapping this information from S and V back onto the data points. So this is telling us how to map from the data points. So this S and the V matrices are really what's capturing this kind of big picture of what's going on. And so what we'd like to do is to create a sketch or an approximation that's just SK times VK transpose. So this is this would give us if we multiply by the relevant parts of the matrix, is going to give a K by D matrix. And we'll call this matrix, let's call this M. Right, so we can get this K by D matrix M. Right, so this would look like, this is K by D, and this is M. And this we'll use to approximate A, from the sense that if you multiply by a d-dimensional vector, it's going to look similar in M as it looks if I multiply by A, in some sense. And I'll be more precise about what that means. Okay, so this seems to be like what you'd want as a good compressed representation of what's going on. It captures the right subspace. Each of the rows of here is kind of a d-dimensional basis vector, and the norm of the row tells you how important it is. So if I look at one of these rows here, see, I couldn't even use this color before. This is great. This row, tells you some direction in a d-dimensional space that the data lies in, and the norm of it tells you how important that is. Okay, so there are a couple reasons why we don't want to actually calculate our approximation this way in all settings. In some settings, if your data isn't so huge, then this is just what you would do. But if your data is bigger, or there are reasons why you would not want to calculate it in this way. Let's kind of list out a few of these reasons. So one is that this is slow for large N and D. Okay, so calculating the SVD of A takes O of N D squared, or it's actually the minimum of N times D squared times N squared times D. So in all of our settings, N was bigger than D, so it's going to be O of N times D squared. Okay, so if the matrix is like, it's like 100 million by 10,000, then this takes about 10,000 times as long as reading the data. And it can be too long on these very big data sets that they have inside of like Google and Facebook and Microsoft. So they don't want to do this sort of operation. So we want to get something that the runtime is much closer to just as fast as reading the data, or maybe reading it a few times. So something closer to N times D. That's one reason. Another is for interpretability. Okay, so if I'm looking at, I'm trying to use these rows of M, this output matrix, as kind of telling me what are the important directions of the data. It turns out each of these rows is going to be a linear combination of all of the original rows, right? So think of one model of this matrix could be that, you know, each column represents a so it could represent a certain thing that's let's see, each column could be, I guess, something that's expressed in a certain gene, and then each of the rows is a gene. Or you could think of each of the column is some item you might buy at a grocery store, and each row is a receipt at the grocery store. So I bought 2 gallons of milk and 6 boxes of Cheerios. You know, I really have the munchies or something, right? And you know, or it could be something else. But if I take a linear combination of these, it's hard to interpret what that means, right? So what you might want to do instead is fill up this matrix with rows from your actual data set. If these are actual genes that kind of give examples of describing a subspace, or they're actual receipts from a grocery store, or if this is a Word document frequency, these are actual documents. You can interpret these a little bit better. So can we use actual rows of A? Okay. Another reason is that the computation might not be centralized. So so computation. And this means a few things. So one could be that we're processing this data in a stream. So we're seeing one row of the data at a time. So we talked about the streaming model mainly with this frequent items problem. where we saw like one IP address at a time, something like that. But what if we're monitoring these documents that we're reading on the web, and they're these kind of the term frequency documents as each row? Well, we're looking at these receipts at a grocery store, so each row is a receipt. And we want to kind of maintain what is a good singular value decomposition, or for PCA or for something else, as this data is coming in a stream. How do we do that? This SVD operation you would call inside Matlab, you give it the whole matrix at once. Right? So if you want to update this, how would we do that? Or let's say the data is too big for one machine. So then there are various techniques actually to compute the singular value decomposition when it's kind of as precisely as you would on one machine if it's spread across multiple machines. But a different way of doing this is to create an approximation on each machine and then combine those approximations together on a single machine. The approximations should be something like this K by D matrix, which hopefully it's small enough you can fit a bunch of those on one machine. So if you're doing really large, you may want to kind of pre-compute parts of it and then move these all into one machine for the different parts of the matrix. Right? So this would be another motivation. And there are various other settings where the data is not all in one place, or you can't calculate it all at once, where you would want to be able to do something like this. Okay. All right. So these are kind of the motivations for various types of matrix sketching, and there are some other ones as well. And so the lecture today will be about a couple of ways of doing this sketching. And what you're going to do, if you look back at this picture, is we're going to create another matrix. We'll call this one B. And this will also have D columns, and we'll use a parameter L for the number of rows. And L might be larger than K, but then you can sometimes reduce it back to K a little bit. Or in some, for one of the techniques, L will actually be a lot larger than K, and another one it'll be, you can make it K. So, but it'll have various other properties that are nice about it. So it will help satisfy these other concerns about calculating the singular value decomposition as this black box. Okay? Any questions there? No? Okay, great. Okay, so we're going to kind of the picture, you have this big matrix A, and you want to map it to a smaller matrix B, which is L by D here. Okay? And so we're going to talk about 3 ways to do this, and 2 of them are going to be today. The first one is going to be called row sampling. And so if you read about this in like some papers or even textbooks, this MMDS textbook that I linked to talks about this technique, but they call it column sampling. They sample the columns instead of the rows, and they think of this matrix being longer and fatter, or longer and shorter. But it's just a transpose. If you transpose the matrices, you end up getting the same thing I'll talk about. The second technique will be this iterative technique that you can think of updating this kind of one row at a time. And we'll talk about an algorithm called so this is called frequent directions. And so we'll talk about both of these today. The row sampling is going to be really simple. You're just going to essentially sample rows from this matrix and put them in this one. But I'll talk a bit more about how you would choose to do that. This one is a little bit more complicated, but it's actually going to look like this. Each agrees algorithm. So it's going to look like the Misha-Gries algorithm for frequent items. And that's why it's called frequent directions. And so it's going to look like this other streaming algorithm we talked about. But it has other nice properties. And then on Monday, the half lecture is going to be about so random projections, where you're going to kind of, and we've mentioned some of this in this locality-sensitive hashing, where we randomly project it onto a one-dimensional vector. We're kind of going to do that at a larger scale in order to map to a smaller matrix B. And each of these will have different set of advantages and properties. So they're all kind of worth knowing. They're all very kind of cute and simple. Okay, so let's first talk about the the row sampling algorithm. Okay. So the kind of so what we're going to do is we're going to have T, and T is going to be, I'll write the asymptotic bound, is going to look something like K over epsilon squared, and I'll explain what K and epsilon turn out to mean in a second. There are some lower order terms I'm not going to go over. So we're going to sample this many rows. So I'm going to sample this many rows independently, right? So what the picture is going to look like is this is A, and each row, some subset of rows, is going to go into B, right? I'll have another one here. Right, so I've sampled 4 rows independently here, and they've gone someplace into B. This might just be okay. So, the question is, how do you sample these rows? How do you do this? And so we're going to set for each row of A. So we'll say for a row in A, and this is going to be a row. We're going to give it a weight equals the norm, and this is the 2 norm of row AI. Okay, so if you remember, it's a row, it's a d-dimensional row, d-dimensional vector. We can take just the distance of that vector, and we look at that squared distance. So it turns out you want to give each of these a weight, and then you want to sample the rows proportional to that weight. Row proportional to WI. Okay. So we had to do this before, right? We had to sample rows proportional to a certain weight. Right? Do you remember this problem? Where did it come up in? It came up in yeah, in k-means plus plus, that's right. So what you can think of doing is you can turn each of these weights into a probability. So W is the sum of all of the weights, and then you just normalize them into a probability. And so then you think of going from 0 to 1, and you have P1, P2, P3, P4, P5, and then say P6. They each take up part of this probability space. This kind of only have 6 here, right? And then I can generate some random, some U is a uniform value between 0 and 1. And if this is, say, 0.45, it goes to P3, and this is the one I sloped. Yeah.
So effectively biasing towards vectors of
greater magnitude?
That's right, exactly.
So why would you know?
Yeah, so that's a good question, right? So think of the axis being here and our data kind of looking like this. And so what I want to do is I want to kind of capture the subspace that this data lies upon. So I can only draw in small dimensions, but if I picked, so let's say I can only pick one of these points, and I picked one with a small norm. If the small norm, so it lies somewhere in here, it might end up being this point, and then the direction I picked would go through this point. This is the wrong space. If I picked one with a large norm, it had to be, say, one far away, and now if I picked this direction, this subspace is closer to what you think is going through all the points. So the ones further away tend to capture where there's the more variation along your data. Right? So I want to kind of, this is essentially the SVD. Remember, if you go back to PCA, you want to center the data first to do this, and after that you model as if the data is centered at the origin, and the more variation occurs with points further away. So I want to find I want to select points that kind of end up being further away. These are capturing the subspace that tends to have the most variation along it. Okay, and so because it's the variance, that ends up being the squared distance that I'm trying to minimize, like the sum of the squared distances, and so that's why I picked the squared norm instead of just the norm. Yeah.
Will this account for outliers? Say you had one far upper left.
Right. So if you have one outlier that's really far away, like if I did have one data point way up here, right? So it's really far away up there. Then maybe it's not so bad actually to minimize the sum of the squared errors. I may actually want to have the subspace go up to that point if it's even further away. But the amount, it turns out essentially the amount I want the subspace to go through there depends on the squared norm at that point. If this one's really far away, but there are a million points that are not nearly as far away, but there are a million of them right here, then I really want to go through this one, even though there's only one. And so what's going to happen is you may have one big thing here and a million small ones, but the million small ones kind of takes up the main probability. Okay, but this works okay. I can do this for it to generate T of these points, or T rows. I should use L here. I use L of these rows because this is how the sketch will work, right? So this is the size L. If I have L of these rows, then I build this once, and then I can generate L of these random variables. So doing this works, but it's not, this doesn't like fit the streaming setting. But there's actually a clever way to fix that I'll tell you in a second. But what it is doing is now each of kind of the vectors I have in B is one of the rows, so I can interpret it. I can say, let's look at the data, and this data kind of tells me these should be a somewhat representative set of data points. So if I look at the other data points, are probably close to some linear combination of these data points. And each of those I can kind of interpret what they mean. So sometimes that's a little bit more useful. People have used this for like understanding some gene expression data, where they wanted to understand which are the actual genes which that correspond with these subspaces instead of these linear combinations of them. Okay, so how would I do this in a stream though? How would I do this in a stream? And let's just worry about choosing one row. I just want to choose one row in a stream.
Can you just keep track of your furthest away row using some bar?
I could, so I could just keep track of the furthest away row, but again, say I had a million points here, and then this row is twice as far, but off in the wrong direction. Then that's not going to give me quite. I want a sample proportional to this probability, just like K-means plus plus. Yeah.
You do it in a range of rows, like between this range and then update it once all of the rows in that range were using an updated range.
Yeah, oh, okay, cool. So this is a cool idea that actually comes up in streaming pretty often. So you think of this is your matrix A, and it could actually keep going down, right? And so you're going to divide up A into a chunk of size that's not too big. Once I've gotten this chunk, I can maybe fit this whole chunk in memory. I'm going to create one random sample, okay? And then I will get, and this will just give me one row. So let's call this just A1 hat, because it's not the original A1, it's the first row I picked. Maybe I'll call this B1. All right, so this is my B1 hat. And then this other chunk, which is not too big, I'm going to random sample again. This is B2 hat. But I don't want to keep both of them. I just want to keep one of these rows. And so then I choose one of these two rows. So proportional to the probabilities, right? If this one, maybe I also kept the sum of all the squared norms here and say this was 100 and the sum of the squared norms here was 200 in this bucket. So then I picked B2 with probability 2/3. Right, so I proportionally sampled one of those two in order to get this new row. And so you can do something like that. You can also grow them. So let's say if the rows were all roughly the same size, then you can kind of ignore this weight. Let's kind of ignore the details, because this technique I'll describe comes up a lot in streaming. And so then you'll just pick one of those at random, ignoring the weights. And so then what happens is I'll get a third thing, and I can't immediately combine this one because it has a different total weight. The squared norm here was 100 and 100, and this is 100. And so I could pick one of these uniformly, but I can't combine that one. So what I do is I wait until I have a third one, or a fourth one, and then I combine these together, and I'll say B11 and or 21, and this is 22, and then I combine these two together. Right, so what you see is you kind of get this binary tree going on here. And what's neat is that if you know your chunk size is small enough, and the size here is always at most n, then the number of active elements I have in the binary tree, I only have at most log n of these actives. The height of this is going to be equal to log n, which is much smaller than n. And so maybe that's okay, right? So if for instance, if I had this other chunk here, B5 hat, then the only ones I needed to have active were this one and this one. There's, at each level of the tree, there's only at most one of these active in my data structure. Now, what would happen is, like, there's really another path here, right? And then eventually this one would merge together, right? There's the rest of this binary tree, but I haven't seen the rest yet. But I only need at least one thing from each of the levels. So it's kind of, this is kind of a neat trick. Okay, so I mean, if you end up looking at a bunch of these streaming albums, you'll see tricks like this come up over and over. But there's actually, for drawing a random sample, there's a simpler way to, in order to do this. There's a simpler trick that's called reservoir sampling. And so I've probably spelled reservoir wrong. I've written this word like 1,000 times in papers, and I think over half of them I spell it wrong. Is it wrong? It is wrong. Okay. Okay. That's not too bad. I've been much worse before. Okay. Yeah, I've like put the R in the wrong well, not the first R, the second, or yeah, usually the second R gets in the wrong spot. But okay, great. So this technique is called so it's called reservoir sampling. And so what you do is you maintain, so say weight I, and this is an uppercase W, is going to be the sum of, so if you're at the ith element of the stream, it's the sum of all the weights you've seen so far. Okay, and you also, so this is something you maintain in the stream, and this is easy to do. You just keep a sum and you add all these things up, right? And so then the other thing is you maintain a point so that you sample. So you have a row AJ, which is your current sample. Okay, and then if you see when you see, let's see, when you see row AI, a new row from A, you set, let's call this B. So this is our sample. So with probability, let's say the weight of I over the sum of all these weights, then you set B equals to AI. Okay? All right, so with probability, the weight over all the weights you've seen so far, you set AI to be this sample B that you have. Okay? So now if you, and how do you do this? Well, you can say I can choose again, some random value U. If that value U is, if I multiply that value U, if the value U is less than this fraction, then I keep it. If it's greater than this fraction, I don't keep it. Right? So let's say this weight was really big, it's 1/2. Or let's say it's 1/3. Then I keep it with probability 1/3. Well, if I generate a random value between 0 and 1, 1/3 of the time it's going to be less than 1/3. Right? So I can easily keep this with this probability. That's easy to do. So why is this correct? Well, there's a nice argument that if you write down the probabilities, they all work out. I'll give you a little bit more intuitive view that's a little bit shorter. So if this was the end of the stream, if this was the last element, then the probability I should have kept this last item, AI, as my sample should have been exactly its weight divided by the total weight. That's going to be its probability up there, right? If I look at how I define these probabilities, right, up in green up there, it's exactly the weight over the total weight. Right? So I've kept it with the last one with the right probability. Okay? And so then, if I did not keep the last one, then I should have kept one of the prior ones. Right? And so if I assumed inductively that B was a random sample from all the I-1 previous ones, then I keep that with the right probability. I should have kept one of those samples. And so then I just need the base case that the first item I see, I keep with probability 1, and so everything else works inductively. Okay, so there's a little bit more to that argument. You can a little bit details to work out, but that's basically it. So this reservoir sampling, very simple, very useful trick. Okay, and so then how this algorithm works in a stream, right? I keep these rows, I select each of them with probability pi. And so I just am going to keep L of these independent of these reservoir samplings. So I might select a row twice. So that's kind of baked into this k over epsilon squared term. That's why I need that many. I'm going to need kind of that many rows, and I'll explain shortly what k and epsilon turn out to be. So this is, I'd like it to only be k rows, right? I'd like to get k rows and approximate this best rank k kind of approximation, but I need this extra factor 1 over epsilon squared, and part of that is because I might sample a row twice. I should really sample this direction, but I sampled something slightly angled off a little bit. So there's some probability of error, or I may have selected this outlier with some probability, so I need to oversample to make sure it works. Okay. You should see this reservoir sampling is very, very simple to implement. Right? So very, very simple to implement. So this is a very, very easy algorithm. Okay, so what does this give me? There's like some formal error bound that lines up with why you get these k over epsilon. So basically what you end up getting is a matrix B, and what you want to, you get this property, and I'll write this down, and then I'll explain what this means. Okay, so you're going to get this property for matrix B. So what does this mean? Okay, so let's start with the easy terms. So this is the Frobenius norm of a matrix. Do you know what the Frobenius norm is? This is often written with squares. This will make it simpler. So the squared Frobenius norm of A is a type of norm. It's just going to be the sum over all ij of. So I look at all entries in the matrix J, I square each of them, and I sum those up. That's the squared Frobenius norm. So this F stands for Frobenius norms. Usually we're seeing 1, 2, 1/2 on the quiz. Those work for vectors. When you have a matrix, how you take norms is going to be different, right? There's different ways you can do it. This is essentially one version of a 2 norm, but if you write a 2, it means something else. Okay. Okay. So and then what is this matrix here? This is again a Frobenius norm, but it's A minus AK. So it's kind of the noise part of that matrix, right? It's the part that's not in this best rank K approximation. So this is kind of the error you get by doing a rank K approximation. It's all of the square of all the elements after you've factored out this best rank K. So you would think if this is a good model for the data, then this is then this should be pretty small. Okay, and so now this is the term that depends on my matrix B, and what this pi of B, this is a projection, so projection of A onto B is what this is here. Okay. So why does this make sense to compare? Well, so this is really defining a subspace. This is equal to, it turns out that you can interpret this as the projection of A onto V, K. Right? So this are the top K right singular vectors I got out of the SVD. This is the best rank K subspace, and A sub K is actually the projection of A onto those subspaces. And so this is the same thing, but using the subspace I found with B. So if I took B and then I took all the singular, right singular vectors of B, then this is essentially, I projected A onto B instead of onto the best ones I found. Okay, so I want this, so if I do A minus this, I want this to be small. if B is of rank K, it cannot be any smaller than this, but it can be smaller than this plus this air term here. Okay, and so that's kind of what the bound says, that the subspace I found with B is close to the best subspace. That's how to kind of interpret this. Okay, and so you need kind of these K over epsilon squared rows in order to get this sort of property. All right, this bound is actually a little bit conservative, but you end up. This 1 over epsilon squared term is kind of annoying. You'd rather be able to not have that term in there. Okay, so there are ways to get slightly better bounds than this, but they end up being slower typically. Any questions about this before I move on to the next technique? You don't necessarily need to understand what this air bound actually means, but this kind of tells you what is possible with this. It gives you about the right subspace by sampling the rows. Okay, so let's talk about this next algorithm now, called this is called the frequent directions algorithm, and so this is a little bit more complicated. I'm going to write down the algorithm in pseudocode. It's going to be about 5 or 6 lines, and then we can kind of discuss. I'll kind of narrate as I go. So we're going to start with the sketch B, which is going to be all zeros, and we'll write this as 2L times D. So it's going to be, I'm gonna kind of just streamline to the fast version of this algorithm. So it's going to be a matrix. So this is the matrix B, and D is here, and this is 2L. There's a way, and so this is going to be our sketch matrix. There's a way to do it with only L rows, but it's going to end up being it's going to be a lot slower. Okay, and so what we're going to maintain an invariant that B is always going to have some row that's all zeros. So it's going to have some row this is just going to be zeros. And if, okay, so now I'll write this as a streaming algorithm, but you can do it in this parallel sense as well. For all AI in the rows of A, right? So we're going to have a for loop. We're thinking of a for loop over the rows. I'm going to insert AI into B. And when I say insert, I ensured there was always an all zeros row, so I'm going to replace those all zeros with the new row. Okay, so if I had a matrix A and I had a B that was big enough, I can just transfer the rows over until it gets full. Once it gets full, then I need to do something. So now I say, if no all zero rows in B, then I need to do something to make some of the rows, at least one of the rows, all zeros. Okay, so, well, what do we know how to do? We're going to take the SVD of B. Okay, so let's take the SVD of B, okay? Now, this is what we wanted to avoid doing, but B is much smaller than A. It doesn't have an n term. So the runtime is now going to be roughly L squared times D. And L is going to be something small. Okay? So this is another color here. This is roughly O of L squared times D time. So even though we're doing the SVD, it's not too bad. Okay. now let's set delta I equals SL squared. So it's the L, so it's singular value of B squared. Right, so I took this, I did this singular value decomposition. I looked at the Lth singular value. There are 2L, there could be up, it was, all the rows were not 0, so it could be up to 2L of them. I took the Lth one. Okay, and now I'm going to change this singular value matrix S to S prime. I'm going to create another diagonal matrix, or diagonal except padded with the zeros at the bottom. And so this is going to be a diagonal matrix, but the elements are going to be S1 squared minus delta I, S2 squared minus delta I, the square root, up to SL minus 1 squared minus delta I. Zeros, okay? So up to the L minus 1 singular value, I'm going to subtract off this delta term. I'm going to shrink the singular values a little bit. And then I do that for this term. This was SL squared already. So when I subtract delta I, this one goes to 0. And all these would shrink to something less than 0 if I subtracted off delta I. So I'm just going to set all these last ones to 0. And now I'm going to set my sketch B is going to be S prime times V transpose. Okay, this is the part that I wanted to approximate with the new S prime. So I've shrunk it a little bit, and now I've multiplied by V transpose, and I get back my sketch. And because I'm multiplying by this diagonal matrix, which is mainly all zeros, now this is going to have L plus 1 rows in it, which are going to be all 0. So I'm going to have freed up a bunch of space. So that means that it's going to be at most L steps before I need to go through this if condition again. So I took the SVD, but I've amortized it out to L steps. So this L times L squared by D is amortized by L. So this costs about L times D times per row. Okay, so this is the whole algorithm, right? It's not too bad. And hopefully it looks kind of like this Misha-Gries algorithm for frequent items. There I had a bunch of these counters and labels, and if I saw something, I incremented the counter, but if all my counters were full, I shrunk all of them. Right? So if instead of having 2L rows, I only shrunk 1 row at a time, I don't get this amortization, but that should look closer. Whenever I add a row and then I do the singular value decomposition, and I shrink the last row to 0 and I shrink all of these. Okay? And so it kind of works kind of like that. What typically happens is if I draw a picture where this is J, and this is the singular value Sj, these are going to kind of tend to decay very quickly, right? And so that's why you usually set these to 0 in the best rank K approximation. Okay, so let's say that L was right here, and maybe these are slightly non-zero. When I drew them, I can only draw so fine on here, right? So this was L. So basically, I wanted this quantity here, this little gap, is going to be delta I, and my new thing is shrinking everything by this gap. So these are my new singular values in S prime. So these are the values in S prime here. Okay, so I just I drew this picture of this ellipse. This was the original matrix B, and then I shrunk it a little bit to get the output this is S prime times B transpose. So I don't care about the U matrix, I just care about the S and the V, and I've shrunk it in a little bit. Right? And so if this decayed really fast, this should actually be a small gap, and the shrinking should be small. Okay, and so it turns out that the error bounds are going to be similar as well to the Michel-Gries algorithm, but you write them out in terms of this matrix form. You can say that for all matrix, for all vectors xd such that x equals 1, that and this is at the end of the sketch. I can have this property here. Okay, so now for any vector x, so for any direction, I look at these ellipses that, and think of this as like the frequency and this as the approximate frequency. But now I get this continuous space of frequency directions, which are these x. Then it's bounded by the sum of all the frequencies. This is the Frobenius norm, as turns out is the right term to use here, divided by L. So if I have more counters or more rows, I get a better approximation. It turns out you can say, and this was actually with the paper with one of my students that we showed this, that you can get a better bound. So you can have it depend only on the tail part. The error only depends on the tail here, the a minus ak. You divide by a slightly smaller term, but you have it depend on the tail. And so then if you set, if L equals to k minus 1 over epsilon, then you have it less than or equal to epsilon times. So if you set L equals k plus 1 over epsilon, so you plug that in for L, you get a 1 over epsilon here, and this is an epsilon times a minus ak. So you get any error you want times the size of the tail with only 1 over epsilon rows. So this works much better. So if you run this algorithm instead, you get a much better approximation of the matrices. It's a little bit more complicated. You're not just sampling these rows. You don't get the interpretability you had before. But this is going to be a faster runtime than computing the full SVD. The overall runtime here, what do we have? The overall runtime of this is going to be O of n times d times L instead of O of nd squared. So if d is like 10,000 and L is like 20, which might be a typical value to run, you get a big savings here. It turns out you can also do a process where you have a really big matrix A, and I can break this into chunks. And for each of these, I can create a sketch. Okay? And so say these are so big they fit on different computers, or that you can capture them at different times. And then I can think of these sketches as being stacked on top of each other. And then I can compress these again into a single L by D matrix. And by the same process on this matrix, which is now length k times L, and I get the same error bounds. It doesn't make the error any worse by doing it this way. I'm just delaying when I do this compression step, actually, so the error does not get any worse. You can also say something about the subspace as well. You can also get a bound that says A minus the projection onto BK of A And so this is setting L equals to 1 over epsilon plus, this is K plus K over epsilon. Okay, so if I run the algorithm with equals K plus K over epsilon, I get this error bound. And now I'm not just projecting onto B, but I project on the first K rows of B, it turns out. So I ensure that I'm only projecting on a rank K subspace. The other one projected on this K over epsilon squared rank subspace. And you get this slightly stronger error bound here. Okay. And so this difference you see in these bounds ends up showing up in practice when you actually run them. This gives a much tighter, much better approximation. But it does not have those same interpretability things. I'm, again, not getting the actual rows here that I got before. So with the row sampling, you're getting the actual rows, which adds to some interpretability. Okay, so let's look back at this again. So this might be something you would implement in your homework. So any questions on how you would actually do this? So how many people have not used Matlab before? Not used Matlab. Okay. So the first question you should have is, oh my gosh, I need to program, like I need to create a data structure for a matrix, right? That seems like a pain, right? Yeah, so like Python has some classes for matrices. C, you really need to build them yourselves probably. I mean, there are libraries, but in Matlab, and you know, I'll try and do this kind of the week after break, I guess. I'll show you a little bit of Matlab code. It's built for the core thing you work with as a matrix. So instead of having just a variable that's a number, you have a variable that's a matrix that's full of these numbers. And so, you know, if you insert a row, you can just actually, inserting a row is just one line in MATLAB. Calling the SVD into outputting 3 matrices is just one line in MATLAB. Right? This is one line in MATLAB. I mean, you can write this in one line, or you could, if you're careful about it. And this is one line. Matrix multiplication is something you can do, right? So each of these is one line, and it doesn't look too different than how I've written it up here. Okay, so the implementing this really is not too hard to do. If you were to write this in C, it's not too hard. You need to kind of have a good data structure for a matrix. Who's written a matrix data structure in C before? Okay, good. So how do you do this? What do you how do you store your data?
Matrix to represent. You have an array of arrays, basically, and you represent it using multiple arrays to represent rows versus columns.
Yeah, so you would, you could have a data structure that has an array here that indexes each of the rows, and then the row is another struct that you call it's just a vector, which is just another array. That's good. That's a nice kind of extensible format. If typically what you want to do is call these libraries, there are these libraries that are written in Fortran that everything uses. MATLAB uses in the back end. You can call them directly from C. They're called from Python and NumPy. And this library is called, it's called LAPACK. And so in LAPACK, you actually don't store it as the structure. You store the matrix as a single array. You just index into it at different points when you want to get to a different row. You jump D elements in the array to get to the next row. So you write it as a single array. And then in order to use LAPACK, you have to figure out whether it wants it stored in rows or columns, and it's kind of a pain to use in C, but you can do all this in C as well. If you use NumPy in Python, it has a bunch of this functionality built in, and in Matlab, everything is just natural. R, I guess, it's very easy to do all this as well. Okay, but the homework will be meant, I think, will probably be written so it's very easy to do in Matlab. Okay, so so let's. There are a couple of points I wanted to bring up about this algorithm and the other one. Maybe some questions you would have. So I kind of explained roughly. Well, maybe I'll kind of. I alluded to the Michigree's algorithm to explain why this works, why you can get this bound here in black. It's not actually, this should be in parentheses. It's this bound instead of this bound. This is not less than this one. Okay, so this should look like the Michigree's bound. Maybe I'll kind of roughly explain why this works. It's not too hard to see, but if you're not used to the linear algebra, kind of the details can be easy to get lost in. But so what's happening is that you're shrinking a little bit in each of these directions. But because I shrunk these singular values, it kind of represents an orthogonal vector here. In fact, if you have a matrix, I guess there's this cool property that I'll write here as this aside here, if it lets me. Let's write this on the side. So let's say that I took the, so S, these are going to be the singular values of A, right? So S is going to be equal to S1, S2, and so on. Okay, then the Frobenius norm of A, the squared Frobenius norm, is going to be equal to the sum up to the rank where those singular values stop being 0 of the squared singular values. Okay, so it turns out that the Frobenius norm, you can write it in this way. The reason why this works is because these are kind of orthogonal components of this matrix, and they tell you how much variation is going on in this direction. And by breaking them into these orthogonal components with the SVD, I've kind of decomposed this Frobenius norm into these parts. Okay? So what's happening is when I'm shrinking, when I'm doing this S prime step, I'm shrinking the Frobenius norm of my matrix B by exactly L, or by at least L times di, times delta I, right? So this shrinks the Frobenius norm by more than L times delta I. And this delta I was this kind of sum, actually it doesn't matter so much what delta I is, that sum ends up being one of the singular values, but there are at least L of these directions, the first L minus 1 and then the Lth one, that all get shrunk by this amount. Okay? But that means if I shrink them all by this amount, and I write if I write this big delta equals by this, then I'm saying I'm shrinking in total across on every step. I'm shrinking the total Frobenius norm of B across all steps, so that the total shrink is more than big delta over L. Right? Because each time I do a shrink, it's little delta I times L. So it's at most big, it's more than big delta over L, because it's the sum of all the shrinks. So that's the total shrink of the Frobenius norm. Okay? But I also know that the total shrink cannot be more than, so this must be less than the total for squared Frobenius norm. Oh no, this total shrink should be times L. Okay? Because each time I shrink it by that. Okay. So then the total amount I shrink must be less than the total Frobenius norm. Otherwise, I would have shrunk more than I had. Okay? But every time I did a shrink, every time I shrunk one of these objects, I shrunk it in an orthogonal direction. I shrunk it a little bit in this way, and I shrunk it a little bit in this way. But those, for any vector, those add up. The total amount they contribute is sums up to 1 essentially. I could, by the Pythagorean theorem, I can decompose the amount I shrink in each vector, and I know that it shrinks by at least the amount I shrunk in any one of these directions. So I know I shrink any one direction across everything from A to B for any direction x by at most delta. Right? Delta is the sum of all of these shrinks. I know I shrink any of these by at most delta. So what I end up doing is I can say that this is less than delta is less, and then delta must be less than this. If I divide L on both sides of this inequality, then I'm going to get this back. So this is how the proof works. And if you're a little bit more careful, you can get this bound as well. Okay, so I didn't quite go through all the details, but if you remember the Michel-Gries algorithm and why that one worked, then this is a similar analysis, but you have to generalize it to this matrix thing. Kind of cool? Okay. What other points I want to make? Yeah, well, let me make a few comments on the column sampling, and then we can wrap up, and then I'll discuss the K-meaning problem if you're interested. Okay, so with this columns, with this row sampling, there's kind of another obvious thing to try and do, which is, you know, if I'm just picking these, you know, I'm picking each of these rows independently of one another. It seems strange if this should, you know, we did the same operation in k-means plus, but there we changed the distance function every time we picked one of these things, right? If I knew I already picked this subspace, then I want to pick things that tend to be away from this subspace next. Yeah, so people haven't looked at that because it's harder to implement in a stream. It's not clear how to do k-means plus in a stream instead. And if you're willing not to do this in a stream, it turns out there are other techniques you can use that do slightly better. but they're typically roughly as slow as doing the Phillips. And only like really, there are ones that you can kind of do fast, but they don't do much better than just doing the norm sampling in most settings. Okay. There are some algorithms that analyze, always pick the point with the largest leverage score and then factor that out and try and do this. And there's some version that try and do this in a stream or in a few passes over the data. And those sometimes work a little bit better, sometimes they don't. So this simple trick of just picking these rows based on the norms works pretty well. If you can do them so you don't pick the same row twice, there's this cool trick which is kind of an extension of reservoir sampling to sample multiple things but with weights. And this is called, and this technique is called priority sampling, or there's a variance optimal that's slightly better than this, but this priority sampling is very cute, and it handles picking multiple things without replacement when they have weights. If you're doing it unweighted, it's pretty simple to do. In the weighted case, you want to use this priority sampling trick. And if you do that instead, then in certain cases, it doesn't do any worse than this, and in certain cases, it will show some significant improvement. Okay. I think that's basically all I wanted to say. So maybe we can end the official lecture here, and then I can discuss some stuff about the k-means algorithm. So sound good? So Pink Font, can you turn the shut this down? Yeah, and then I don't want